Okay, so we're going to start now. Hello, my name is Michael Battalia, and this session is regarding the presentation for developing for the Commodore 64. So I did start a poll a little while ago. Actually, I'm going to switch that poll and see how many of you actually have the Commodore 64 growing up. Actually, most of you people did grow up with the Commodore 64. I'm not sure if you guys can see the results, but a third of you guys said you had the bread box version. Actually, that second one's supposed to be the C64C. I misspelled that one. I'm not sure if everyone really got that. And 25% of you said you did not have one, so I feel sorry for you guys. But I'm assuming you guys are here now, learning to see what is going on. Great. I also have an original Commodore 64 right next to me as well. Okay, so let's get started. So some of you actually are here probably just starting to learn the basics of how to program for the Commodore 64. However, some of you probably already know how to program the Commodore 64, and maybe this is just a refresher course for you. Either way, I hope you guys have some fun and may actually learn something new. So this presentation I've outlined right here in terms of the topics I'm going to discuss. So first, I'm going to talk a little bit about myself, who I am, how I got into programming. And then we're going to talk about why I even program for the Commodore 64 to begin with. And then we're actually going to discuss the Commodore 64, a little bit about the history and some of the technical specifications and features. And then we're going to talk about what you need to learn and know about in order to get started in programming for the Commodore 64. And we're going to jump into some actual coding examples, which will be very exciting. And then we're going to discuss some next steps that I would recommend that you would take once you have the basics of programming down. And finally, going to wrap up with some Q&A. Okay, so I'm going to talk about myself. So again, my name is Michael Battalia, and I've been programming for pretty much most of my life. It started off in the mid-'80s when I was about 5 or 6 years old. We had the Texas Instrument TI-99, and it came with BASIC. Admittedly, I didn't know what I was doing at such a young age, but I learned programming at that point simply just by copying programs out of textbooks and putting them to the computer. However, we didn't have a way to save programs, so every time we turn off the computer and turn them back on, we'd have to re-enter them in there. And again, immediately, I didn't know what I was doing. But I really didn't start understanding programming until the late 80s when I started elementary school. And at that point, our parents got the Commodore 64. I programmed in BASIC version 2, which was the language that you could program in right away when you turn on the computer. Admittedly, my parents probably spent a lot of money on the computer because we also had the 1541 disk drive, which allowed us to load and save programs off of 5.5 floppy disks, which was great for me trying to learn programming. So I was able to save my programs and load them back up and continue programming. So I was able to kind of build up a little bit more on that experience. However, the age of Commodore 64 kind of dawned on me for a while after that point, because around junior high in the mid-'90s, I got my first PC. And by then I was running Windows 3.1 and DOS 6.22. And I started learning how to program in QBasic and Visual Basic, version 6, and C++. And for the rest of that decade of the 90s, I did what most people did at the time, and that is just upgrade your PC, went from Windows 95 to Windows 98. And at that point, I just continued working on to learn Visual Basic 6, and even to this very day, I still program in that language. And around the turn of the century is when I entered in college, and by then I started learning some more advanced programming, some more advanced topics in C++, Java, C#, and I also started learning how to program on some of the mobile devices that existed at that time, which was Windows CE and Palm OS devices. And then after that, through the next decade, from the 2010s through today, newer operating systems such as Windows 8, Windows 10, and now I'm working as a full-stack developer for a small programming firm, programming in, again, Visual Basic 6, C#, ASP.NET. However, in my downtime, I program for mobile devices such as Android and iOS, and including assembly language, which covers x86 and 6502, which is going to be the language we're going to be discussing during this presentation. Okay, so you might be asking yourself, why program for the Commodore 64 specifically? So the real answer is, first off, 8-bit computing never really went away. In fact, more recently, there's been a lot of reinsurgence in terms of this type of era of computing programming. A lot of hobbyists have kind of dusted off their old 8-bit computers and consoles out of the closets and out of their parents' homes and took them home and just kind of see like, hey, this is great. This is very nostalgic, but what else can I do with it? Maybe I can like take some new features and stuff that are kind of like around today and kind of expand on the capability of these old computers. In fact, you can go ahead and you can download a lot of basically an emulator for practically any 8-bit computer or console that has ever existed and just run them on your computer. Many manufacturers, including Nintendo, have like re-released some of the old classic consoles. For example, the NES Classic, which is a smaller form factor of the original NES console. Running an emulator inside, you can play original NES games. A manufacturer also released the Commodore 64 Mini a couple years ago, which basically had the same idea as the NES Classic. Smaller form factor running a Commodore emulator inside a device. And last year they released the C64 Maxi, which is almost an exact replica of the original breadbox version. Again, you can run Commodore 64 games on it inside of an emulator. You can even program on it using BASIC. Another reason why you want to program for the Commodore 64 specifically is because the Commodore 64 is the highest single-selling computer of all time. It's sold between 12 and 17 million units worldwide. It has a huge user base, even to this very day. And another reason why is because many new games and demos are still being created to this very day. So if you do write a program for the Commodore 64, people are going to be able to play your game. In the next couple slides, I'm going to highlight a couple of the new games that came out in recent years that you can play on a Commodore 64 today. So the first one I'm going to highlight is a game called Planet X2. So this game was released in 2017 by a developer called David Murray. In fact, I believe he's in chat right now, the 8-bit guy. This game is a real-time strategy game. If anyone's ever played a game like StarCraft, it's very similar to that. You control units that can build and build buildings by mining resources. You would have to defend your buildings from attacks from enemies, as well as attacking the enemy in order to beat the level. The next slide I'm going to highlight, which probably most people are familiar with, is Super Mario Brothers. This particular port is called Super Mario Brothers 64 and was released in 2019 by a developer that goes by Zero Page. The developer took 7 years to actually make this game. It's like a true 100% realization of the original NES Classic game. However, it's hard to find actual copies of this game now because Nintendo did send the developer a cease and desist letter because they didn't have the licensing to release this game. However, if you want to see the full walkthrough, there is a video available on YouTube. The last game I want to highlight is called Fix-It Felix Jr. Now, if anyone's familiar with the Pixar movie Wreck-It Ralph, then you know what this game's about. This game came out this year, actually, by a trio of developers, and this game is about the hammer person there at the bottom. His name is Fix-It. He's trying to repair the apartment building being destroyed by the guy at the top knocking those blocks down. His name is Ralph. And this game also has digital sound in it where you can actually hear Ralph saying, "I'm going to wreck it." And again, all these games, they're available online for you to download, and you can run inside the emulator or play it on an actual Commodore 64. Okay, so moving on. Now we're going to talk a little bit about the Commodore 64, a little bit about its history, and mostly going to highlight the physical attributes of the machine itself. So the Commodore 64 was released originally by Commodore Business Machines in 1982. Originally sold for $595 US. However, the price was reduced to approximately $300 the following year. The Commodore came with a 6510 CPU, which was a small variant of the popular 6502 processor, which was a very popular CPU at the time. It was included in the Commodore 64, the NES ran it, and so did the original Apple computer. It was an 8-bit processor, where the Commodore ran it at approximately 1 megahertz. The speed of the CPU largely depended on which region you purchased it in. So, for example, if you purchased the Commodore in the North American region, you would get the NTSC version. However, if you purchased it in anywhere else in the world, you would get the PAL version. And the NTSC version ran slightly more than 1 megahertz, and the PAL version ran slightly below 1 megahertz. And that was related to the refresh rates of TVs at the time in different regions. It also came with 64K of RAM, hence the Commodore 64. It had 20 kilobytes of ROM, which we'll talk a little bit about in a future slide. However, it also came with a bunch of hardware registers. Each register had a specific purpose. So the A register is known as the accumulator. All the math was done against that register. You had two general registers called X and Y, which the programmer would just do whatever they want with those registers. They had a processor state register P, a program counter register PC, and a stack pointer register SP. For this presentation, we're only going to talk about the A, X, Y, and P registers. The Commodore also had a video chip called the VIC-2, which stood for Video Interface Chip 2. It came with 16 color support, had 8 hardware sprites, and used a map memory scheme. The video chip had multiple video modes. The two most common is called character mode and high-res mode. And in both modes, each graphics mode had a grid of 8 by 8 pixel cells. And inside each grid, depending on which mode you can do, by default, only supported 2 colors. So the first mode, character mode, had a grid of 40 columns and 25 rows of these 8 by 8 pixel cells. In high-res mode, you had 320 by 200 pixels, but again, you can only display a total of 2 colors in each 8 by 8 cell. There was ways to increase that to have 4 colors, known as multicolor modes. However, it did reduce the total number of columns you can have in terms of each 8 by 8 cell. The Commodore also had an audio chip called the SID, which stood for the Sound Interface Device. It only had 3 voices, but each voice had a complete what's known as an ADSR envelope, which stood for Attack, Decay, Sustain, Release. And because of that, it was able to create very dynamic sounds. In fact, a lot of people arguably consider the SID chip of the Commodore 64 having the best sound from any other computer of this era. Okay. So up here on your screen right now, you should see the two there's the 2 models that were available to consumers back in the day when purchasing the Commodore 64. The one on the left has been known as colloquially as the bread box version because it looks like a bread box. This was the original version that was released back in 1982. The only thing that's different here is the function keys. Some models had a different color. Some were like a light yellow color. This one is a grayish color. This is actually the one that I have. Looks just like this one. In 1986, Commodore released the Commodore 64C, which had a different form factor. And not only did it look different, but also included lower voltage chips inside, so it was less likely to fail. The reason why Commodore released this newer model was because the prior year they released their next computer, which was called the Commodore 128, and they wanted to release a version of the Commodore 64 which looked more like the Commodore 128. However, both computers can feature-wise are exactly the same. They can run the same hard programs. They're compatible with programs that were written in one or the other. Okay, so moving on. Before I mentioned that the Commodore had 20 kilobytes of ROM, however, 26 kilobytes of the RAM of the Commodore 64 itself was reserved for special things to make the computer actually run. And of those things are actually outlined below. It was reserved for the basic ROM, which had the basic language in it, had its own kernel, which would have a whole bunch of set of libraries, for example, like displaying characters on the screen or communicating with the disk drive. ZP, which stands for zero page, that's a special area block of memory, the first 255 bytes of memory, which is reserved mostly for work, for the kernel libraries and basic. Another part of memory that was reserved was called the stack. And then you also had an area of the memory reserved for I/O, and lastly, the character ROM. So if you take the 26 kilobytes of memory and you subtract it out of the total 64, it leaves you with a total of 38 kilobytes of RAM available to the programmer. In fact, if you draw your attention to this bottom screen right here, you'll see that this is basically what always shows up every time you turn on the Commodore 64. The user's greeted with this message saying Commodore 64 with basic version 2, total of 64K RAM in the system. However, only 38,911 basic bytes free. You could also, there are ways to switch out and turn off the basic and kernel to get that additional 16K of RAM they can use. However, if you did that, then obviously basic wouldn't work and those kernel libraries just weren't available to your program. The next slide, I have a graphical representation of what the total RAM of the Commodore 64 looks like with the ROM kind of overlaid on top of it. So again, you can switch out this basic ROM to get this RAM available more to the programmer. And then you can also have this kernel as well shut off. These two blocks right here equate to, they're 8 kilobytes of RAM each. And you have the character ROM and the IO area kind of like overlaid on top of each other because there's special flags that kind of turn on and off the basic different areas of RAM where you want those things to be loaded. I'm not going to talk anything about how that works. I'm just kind of showing you how the memory is laid out. Okay, so let's talk about programming. So first, I want to just outline some tools and some knowledge that you're going to need to be familiar with in order to get started. So we're going to embrace the concept known as cross-development. So even though you can program directly in the Commodore 64, I highly recommend for somebody who's just starting out to basically try to get the programs working on a PC first. Get it working inside of an emulator. And then once that works, then you can get it working on an actual hardware device, which at that point would be much easier because the emulators that exist nowadays are extremely close in terms of functionality of an actual Commodore 64. So the first bullet point I'm going to highlight is an emulator. So this emulator is very popular for the Commodore 64. It's called VICE, which stands for Versatile Commodore Emulator. And there's the link there. Again, you can also Google this. I'm going to post these presentations notes online in case you guys want to refer back to this. But again, there's a link. It's a free download. The next bullet point is the environment, the programming environment that I would like you guys to kind of look at in terms of get started for programming. This one is called CBM PRG Studio. Again, it's a free download. It works on Windows. And also, you'll need to be familiar with is 6502 Assembly Machine Language. We're going to be talking about some of the instructions in terms of and concepts in order to get started with assembly language in these slides, but we're not going to talk about it in great detail. Lastly, again, optionally, if you want to run your programs on an actual Commodore 64, you would probably going to need some sort of hardware to get the programs off of PC and loading inside of a Commodore 64. And personally, I use the SD2 IEC device, which loads a Commodore program onto an SD card. However, there are many other ways to get the programs on there. So some of you might be asking, well, why program in assembly language at all? So in this slide, I'm going to discuss a couple of the pros and cons of that. So first, the pros. One of the big reasons to program in assembly language is it's very fast. So you basically only have two choices when programming the Commodore 64. One's basic version 2 and the other one's assembly language. And basic version 2 is easier to understand and program in. It's much slower. And as I mentioned before, the Commodore is only running at 1 megahertz. So you want to try to get your programs running as fast as possible. And assembly language is the fastest way because the CPU is executing your instructions directly. And that brings us on to the second point. You have the highest level of control. In fact, there's a lot of really special and amazing things you can do with assembly language which otherwise you could not do with basic. When people write games and they do demos to do some really complex, amazing stuff with the Commodore 64, assembly language is the language of choice. However, there are some drawbacks to learning assembly language or programming assembly language for the Commodore 64. And one such is that it's harder to read and write assembly language. In fact, just by looking at a bunch of code written in assembly language, sometimes it's kind of complicated and gets confusing in terms of just figuring out what a certain routine does or what the program does as a whole. Another drawback is portability issues. So what this means is that if you have assembly code that's written for one compiler and then you try to get it run on a different compiler, sometimes it doesn't work. And the reasons for that is because over the last couple decades, new compilers have been created. However, there's been a lot of misleading or inconformity to how instructions are supposed to work or how branch codes are supposed to work from one assembly compiler to another. However, that being said, CBM PRG Studio has a pretty high level of degree of portability. So even if you do copy a code example off the internet that was written in a different compiler, chances are it will compile in that CBM PRG Studio compiler. And if it doesn't, it may require some minor modifications to the code. So in order to really jump into the assembly language, we need to understand different numbering schemes. So there's 3 numbering schemes I want to just talk about first. The first one's called decimal. And everyone should really be familiar with decimal already because decimal is the numbering scheme that basically everyone uses on a daily basis. It's known as a base 10 numbering scheme, which means that the digits go from 0 to 9. And an example over here, I should kind of show you what a decimal number would look like in code. So it's just a number you type out. And this is different from different numbering schemes because different numbering schemes require a prefix to be before the number. And that brings us on to the next number, binary. Binary is a base 2 numbering scheme, which means that the digits only go from 0 to 1. This is also commonly referred to as a bit. In this example to the right over here, I show that a binary has a prefix with a percent sign. The last scheme I want to talk about is called hexadecimal. And hexadecimal is a 16 base numbering scheme. The digits start from 0 to F, and the letters basically mean any digits that are greater than 9. So A, B, C, D, E, and F are 10, 11, 12, 13, 14, and 15. Hexadecimal numbers have a prefix of a $sign. So again, these prefixes are very important in order to indicate which numbering scheme that you want the compiler to recognize for this number. So now we got the schemes out of the way. We're going to talk about data types. So there's 3 different data types that we're going to cover. The first data type on the bottom over here is called a byte. And a byte is an 8-bit number, meaning that it's comprised of 8 binary digits. It has a number that ranges from 0 to a maximum of 255. So in order to figure out how to actually figure out what a byte number actually is, what you need to do is you need to see every time that there is a 1 in the digit of a binary, of a byte number, what you need to do is you need to take that digit and raise it to a power of 2 minus that digit. For example, for the first digit, which has a 1, that's going to be 2 to the 0th power, which happens to be 1. The second digit is going to be 2 to the first power, which is 2. And then you keep going on and on until you get to 2 to the 7th power. And once you figure out what those values are for each individual digit, which I have outlined over here, you're going to add all these numbers up together. And then once you do that, you end up with the decimal representation of that byte, which in this case, because it's all ones, equals 255, which again is the maximum value of a byte. Moving on, so another data type I want to talk about is called word. And a word is a 16-bit value. And basically what this is just 2 bytes just put together. And when they're put together, they have a value of a range that could be anywhere from 0 to 65,535, which happens to be 64 kilobytes. And this is a very important number because this number will allow us to reference different parts of the memory, which we're going to be using later on when we look at code examples. So in order to figure out what comprises a 16-bit number, just think about it this way. We take 2 8-bit numbers. So the first one's called a low byte, or also known as the least significant byte. And it's just like the last example. You start from 2 to the 0th power, and you go all the way to 2 to the 7th power in order to figure out what that value is. However, the second part is called the high byte, which stands for the most significant bit. This one, you don't start from 0. You just continue on with the next order of the base. So in other words, you go to 2 to the 8th power all the way to the 15th power. And once you figure out which ones have 1s in there, and then you get the 2 to the whatever that digit power is minus 1, you add all those digits up, and then you get the decimal value of that 16-bit word. The last data type we're going to talk about is a 4-bit one called a nibble. And the only reason why you need to know about this is because this is for representing a hex number. Hexadecimal number in binary, or rather in assembly, is comprised of 2 nibbles. So you have the high nibble and the low nibble. So in this example over here, F and A, F is considered the high nibble, and A is considered the low nibble. And when you put them together, you get an 8-bit number, which is, again, a byte. So in order to figure this out again, you would just take 2 to the 0th power, all the way to the 3rd power to figure out the low nibble, and 2 to the 4th power, 2 to the 7th power to figure out the high nibble. Most of the time, people don't really care about what a nibble is. But again, I'm just kind of showing you that the high and low nibble represents a hexadecimal number, which equates to 1 byte. Okay, moving on, we're going to talk about opcodes now. So there's a total of 56 different opcodes in the 6502, and I'm going to talk about a couple of ones right now. So the first one I talk about is LVA, which stands for loads value into the accumulator. And what that does is just takes some value that you have as an argument after LVA and just throws it into that A register, again, the accumulator. The next instruction I want to talk about is called STA, which means stores a value from the accumulator and then throws it into memory. So in this code example I have outlined below, what we're going to do is that we're going to load the value, decimal value 2, into accumulator. Now, something I also want to talk about real quick is this pound sign. So this pound sign right here means that we're going to take this immediate value 2. If we didn't have that pound sign there, that means that it's going to load the value out of memory. So we don't want to do that. In this case, we just want to load the value 2 to the accumulator. And then in the next line, STA, we're going to take that value out of the accumulator, which is 2, and we're going to store it into memory. In this case, we're going to store it at the hex 400. That's the address we're going to store that value. So what these two lines of code are doing is simply just copying the value 2 and putting it to memory location 400. Now we're going to take the next two examples, and now this time we're going to load the value out of memory location 400 hex. So in this case, you see it does not have a pound sign here. And again, that's because the pound sign indicates we want to copy the value. If we had a pound sign here, it means that it's going to try to copy this value into the A register. But in this case, since we don't have the pound sign, it's going to copy the value out of the memory address that's stored at 400 hex. And then the last instruction is going to take that value that was stored from 400 hex that's now in the accumulator, pull it out of the accumulator, and put it into 401 hex. So what these two lines are basically doing is copying the value out of memory address 400 hex and put it to 401 hex. Okay, so just kind of brushing back to what we were talking about in the last slide, I just want to talk really quickly about the different types of ways that you can call LDA. So again, just refreshing here, the 0 page, this is the first 255 bytes of RAM. And the reason why that's important is because I've kind of outlined here in parentheses the different number of cycles at each different ways you can call the LDA instruction. So again, the first one's an immediate value. We're storing the value 2 in the accumulator. That only takes 2 cycles. The second one, we're copying the value out of the 0 page area, specifically at a memory address hex 2. This one takes 3 cycles. And as the last example, we're copying the value at 2000 hex. This is basically copying the value from anywhere else in memory. This one takes 4 cycles. Now you might be asking yourself, well, why do I care about the cycles? Well, when you program in the Commodore 64, again, it being a very slow computer, you're going to have to keep in mind how many cycles each instruction costs. And this becomes very important when you're doing things like creating a loop of code that goes through a lot of instructions that have heavy cycles, because that could really slow down your program. Okay, so another concept I want to talk about is indexing. So in this case, I have an example of code. There's quite a bit of code going on here, but I'm going to break it down for you. So indexing is going to do is allow you to pull a value out of an array or a list of variables which are stored in memory. So in this first line of code over here, I have this what's called a variable. And what a variable, you can think of it is kind of like a pointer to a different part of memory, so that when you refer back to that variable, that your compiler knows exactly where in memory you're referring to. So in this case, my list has a list of bytes. So a byte over here indicates a data type. So I have 8 bytes over here, just some random hexadecimal values. Now let's say I want to pull the third item out of this list into the accumulator. So to do that, what you want to do is that you would need to utilize some new instructions. The first instruction I want to introduce is called LDX, which is similar to LDA, but instead of storing the value into the A register, now it stores it into the X register. Remember before, we have 2 general registers, X and Y. And the reason why I store the value 2 here is because in computing, it has what's known as a zero-based index. So if you want to get a particular element out of a list, you have to subtract 1 from that element number to get the index number. And then on this next line, I have LDA, right? I have a variable, my list, but now I have another argument called comma X. And what that means is that it's going to use whatever value stored in the X register as an offset to populate the accumulator. So in this case, it's going to pull the third element from the list and store in the A register. I also indicated over here the number of cycles this instruction takes. The next part of code over here is going to do similar to what it was doing before. However, it's going to be using what's known as an indirect index. And what indirect index basically means is that it doesn't have like the my list variable referenced directly in the LDA instruction. Instead, it's going to point to a block of memory where the address for my list is stored. So in this case, I have these bunch of instructions over here. And what I'm going to be doing first is I'm going to be taking that variable and I have to separate the high and low bytes of the my list. Now, this is kind of a very important concept, so I'm also going to break it down in the next couple slides. So my list is a 16-bit value because in the Commodore 64, we have 64 kilobytes of RAM, which is a 16-bit value. However, the CPU itself is only 8-bit, so it can't take a full 16-bit value at a time. You have to break it apart to its high and low bytes. And in order to do that, the compiler has these directives to kind of make that easy for us. The first one is this less than sign. This less than sign gets the low byte out of the address. And then we're going to store it just in some zero-based memory address, in this case, FD. And next one, I'm going to use this greater than sign to get the high byte. And now I'm going to store it in FE. And it's important that I store it in FD and FE, which in memory are right next to each other. And the reason why that is because when you call the LDA function, it's going to only reference the low byte. So internally, the CPU is going to assume that the high byte of the memory that stores the my list address is going to be the next byte after it, which in this case is FE. Similar to what we did above, we're going to store the index. This time we're going to store it in the Y register. So in this example, since I'm storing the index value 6 in here, which means I'm going to get the 7th element in the list. And on this LDA function, you can see there's a parentheses over here, which indicates an indirect reference. Again, we're going to pass in a low byte, and then we're going to pass in Y as the last argument, which has the index number. And this instruction costs 5 cycles. So as I said before, I'm going to break it down a little bit more about that high and low byte breaking down. So over here, I'm just kind of indicating what it looks like in memory. In this case, I just have like some direct hexadecimal number. Again, it's a 16-bit value. That's what's important. So I want to get, this first line over here is going to get the least significant bit. So that's what this less than sign is. So it's going to copy 0, 1 to X register. And then on this line, it's going to copy 0, 1 into this memory location FD. And its last two instructions are going to get the most significant byte, which in this case is 4, and store into memory location FE. Another thing I want to talk about is self-modifying code. So this is one of those things that you can do only in assembly language, where you can write instructions in your program in a way that will actually modify your code of your program while it's running. Now we'll talk about why this is useful in some of the upcoming examples, but I just wanted to just show you real quick like what actually is happening here and what that means. So I have some code over here on the left side, and on the right side I have like a memory dump of what these, specifically what this first line of code is actually going to be doing. So what I want to do is I want to change this address right here, this argument. So when I compile my program, it starts off looking like this. So first we have this opcode. So 99 hex represents this STA instruction. And then first we have the low byte, which is 34 hex, which represents this. And then we have the most significant byte, 12, which represents this. And basically, you might notice the order is reversed. It's kind of weird. It shows the low byte first and the most significant byte. This is just the way that the memory is laid out in the Commodore 64. It's called little ident. It's actually a very popular scheme that most computers do. But on these instructions over here, similar to the last example, I'm going to get the low and high bytes and store into a register. However, this time, I'm going to include what's known as a label. So what a label is similar to a variable, which is a pointer to a particular memory location. So in this case, label points to the memory location of where this opcode is stored. But I have this offset over here, +1. And what that means is it's going to offset that value by a byte. So instead of storing the value 1, at where this is located, where the STA is located, it's going to store it where this first argument is, which is the low byte. So this line changes this argument from 34 hex to 1. And then similarly, on these last two lines of code, it's going to take the value 4 and it's going to put it into the high byte argument. So at the end of this result, what's going to happen now is that this STA function is no longer going to store the value at memory location 1, 2, 3, 4 hex. It's now going to store it in 0401 hex. Okay, so moving on, we're going to talk about flow control now. And basically what this means is it changes how your program runs in terms of jumping to a different part of code in memory. So there's a couple different ways to do that. The first one you can do is an unconditional jump. This instruction is called JMP, and it just jumps to a different part of memory. That's all it does. It's similar to a go-to statement if you're familiar with basic programming. We also have another one called JSR and RTS, which stands for jump to subroutine and return from subroutine. This is similar to jump, but instead what it does is that the CPU will store the address of the next instruction after the JSR call, so that when you jump to a specific spot of code, and it will allow you to jump back to where you were before. And this what allows you to do is create what's known as subroutines. And subroutines are blocks of code which can be called multiple times in different parts of your program. And we're going to be showing some examples about that later on. The last one in flow control is called branches. And branches let you jump to a different part of memory address conditionally. And the condition is based off the value of the bits stored in the P register. Now, if you remember earlier, the P register is commonly referred to as the processor state. And the processor state changes based on the result of the last instruction that was just executed. So down below, I've indicated each bit of the P register. The P register is just 1 byte. The only bit I'm going to be talking about during the presentation that we care about is the 0 flag. And a 0 flag bit gets set only if the result of the previous instruction was 0. So for example, if you wanted to branch to a different spot of code, if the last instruction result was 0, you would use the BEQ branch. And again, we're going to be talking about branches in the next couple examples. Okay, so here we go. So I'm going to talk about some examples. First, I'm going to talk about CBM Computer Studio, and so we're debugging it. We're going to switch to that program momentarily. They're going to show you some examples regarding indirect indexing versus self-modifying code. Then we're going to write a string to the screen. Then we're going to talk about subroutines, and lastly, printing multiple strings to the screen. Okay, so I'm going to now switch over to CBM PRG Studio. And here it is. I have some basic code already typed up for us. There's a couple things I just want to first talk about. First off, this assembly program right here, how it's outlined is kind of just a very basic program. The very top over here, every program has to have. This is known as the entry location of where your program will be loaded up into memory in the Commodore 64. So this first line of code over here, it says star equals $C000. That means that this program will be loaded into memory at location C00 hex. Sorry, C000 hex. Next, I have this label called main. I just put this here as a label just to indicate where my main body of my code starts. This is not required, but I just keep it there just to keep my code looking nice and neat. And lastly, we have this RTS. And if you remember before, RTS means return from subroutine. So if this is the only subroutine you have in your program, then it's just going to return back to basic when your program's done. Now, I have some commented out code over here. So the semicolon character in assembly basically means that this is a comment. This code won't be compiled. However, I'm going to undo this comment so I can just see what's going on. So I have some instructions over here. It's similar to the instructions or the sample from the previous slides. We're loading a value into A register and storing to memory. But I want to debug this code. And CBM PRG Studio has a built-in debugger, which makes it really cool to just step to your program and see what it's doing before even running it inside of an emulator. To start the debugger, you press F8. It'll compile your program really quick, and a bunch of windows should pop up. So at this point, if you're watching the presentation, I recommend probably full screening the screen because some of these windows are a little bit small. But I'm going to just move my mouse around so you can follow along. This first window over to the left over here is called the debugger. And the first thing you want to notice at the top over here is this breakout of the different register values of the Commodore 64. Again, this is just kind of running like as a kind of like a fake emulator. So everything has like a default state. But we can see basically to get the program counter, the accumulator, the X register, the Y register, the stack pointer, and we got status register. This is the processor state. And then it breaks out this value over here so you can see the values of each bit of the processor status register. Down below over here, this is your code that you just compiled. So this shows you your code as it's running in memory. So it has over here the raw bits, the raw bytes, and then it shows your instructions over here. To the right, you have the video RAM, and the video RAM shows you essentially what the user would see on the screen. However, you see it's a bunch of @ symbols. The reason why it's a bunch of @ symbols is because it's the @ symbol relates to the character of value of 0. This is when you turn on the Commodore, you don't see a bunch of @ symbols, but again, this is like a fake emulator. So, and then lastly, you have the memory viewer, which shows you a raw dump of the memory. So we're going to be looking at this in an example a little bit later on. But I want to start stepping through some code now. So the first instruction, LDA, is going to store the value 1 into the accumulator. Now, some of you might be asking, well, aren't we starting to store the value A, not 1? Well, it so happens that A means 1 to the Commodore once you compile it. So what's happening here is the compiler is already taking the value A and just putting it to in this case, a hexadecimal number for us. So to step through code, I'm going to press F7. And I want everyone to look at the value of the A register as I do that. So now you can see it changed from 0 to 1. Okay, great. And the next instruction over here, it says STA004 is going to store the value into memory at that location. However, it's not just some random memory address. I know by default that location is where the video RAM is for the Commodore 64. So what this is going to do is I want to print that character onto the screen. So if you look over here in the video RAM, what memory address 400 hex here is this first column and first row, this character right here. So if I press F7 now, you'll see it printed the character A there. Now I'm on the RTS line. If I press F7 one more time, it's going to jump to memory address 0. And in this case, in the debugger, that means your program's done. So you can just close out the debugger at that point. So great, perfect. But I want to actually see this program actually running on an emulator. So CPM Preacher Studio does let you do that. If I just press F5, and I'm going to close out this assembly dump. I'm going to come back to that a little bit later on. But for now, it should start. Here we go. Starts the emulator. It pressed run. Well, nothing happened. Well, the reason why nothing happened is because run only executes basic programs, and we wrote an assembly program. So in order to run an assembly program, we have to type a special command called sys, and then we need to type in the starting address. So in this case, the starting address is C000 hex, but we need to convert that to decimal, which I already did up here. So you type sys 49152, and you press enter. And now you should see that printed the character A up here. All right, I'm going to comment this out now. I'm going to unremark out this block of code. And I want to step through the debugger one more time with this new example. And this new example, what it's going to do is going to now do a loop, and it's going to print. It's actually going to go through all the characters of the Commodore character ROM, which is known as PETSCI, and print them onto the screen. So the first thing I want to do, I just want to put that first character into the accumulator like it did in the last example. So I'm going to do LDA1. I'm going to step through that. So now the accumulator is 1. I'm going to store it onto the screen just like the last example. I'm going to press F7, and now you see the video RAM is updated to A. However, this next line is something new. The instruction is ADC, and ADC means add with carry. And for this example, all you need to know is I'm just going to increase the value of the accumulator by 1, and the 1 is this value right here. So if I press F7, you'll now see the accumulator change from 1 to 2. On this next line, I have this branch called BNE. This means branch if not equals. And what this means in terms of the processor state, if the processor flag 0-bit is not set, it'll jump to that that address. In this case, it's going to jump to loop. So since the value of the last instruction was 2, it's going to jump back up to loop. So press F7. Now jumped up to loop. And now it's back at the store statement. It's going to store the value of the accumulator at that memory address. However, the accumulator is now 2. It's no longer 1. So let's see what happens now if I press F7. So now you can see the value of A changed to B. I'm going to close out the debugger because it's just going to keep on going until it reaches a value of 0. And that happens because when you keep increasing an 8-bit value, it will overflow. And once it overflows at the value 255, it loops back around to 0. And when that happens, this BNE branch won't actually execute. It won't jump back to that loop. And instead, it'll just exit your program. OK, so moving on to more complex examples, we're going to be talking about indirect and indexing and self-modifying code. So these two blocks of code do exactly the same thing. And what that is going to print the character A onto the screen 255 times. So I'm going to start the debugger one more time. Okay, so the first 4 lines of code, what it's going to be doing, it's going to be storing the memory address 400 hex into memory. And in that case, and just like the previous slide, so we can do an indirect memory store. So I'm going to press F7 to get past these couple of lines of code. And then we're going to start by setting the Y register to 0. So this is basically saying, oh, we're going to start offset 0. I'm going to start the LDA with default value 1, which again is A. And now I'm going to store the indirect value of that stored FB and FC with offset Y with the value stored in the A register. So what all that means is that we're going to store the value of the A register into the memory location starting at 400 hex. So if I press F7 again, you'll see it shows the A in the first character in row. Now here's where things get different. So I have this new instruction called INY. And what INY does is it increases the value of Y by 1 and increments it. So now the Y register is currently 0, and I press F7, now it's 1. And because 1 does not equal 0, the B and E branch will jump back up to loop. So now we're back at this STA variable. So, but now the offset is now 1. So what's going to do is going to take that memory location 400 and it's going to add 1 to that. And what that's going to do is should print the character A to the next column. So press F7. Now you should see there's 2 A's on the screen. And again, this will just keep on going until it reaches 255 bytes in the Y register, and then it'll just exit out. However, before I exit out of the debugger, I want everyone to look at this other last instruction label right here. I don't know if you guys can see it. It might be pretty small. But this last instruction label shows you the cost of that last instruction. So this STA variable costs 6 cycles. I want everyone to remember that as I show you the next example. So this last part of code over here, this again is self-modifying code. I'm going to press F8 on it, bring up the debugger. And what's different over here is a couple things different. The first thing is that instead of storing the address of 400 hex into some 0-page address, we're going to store it into memory location C00F and C010 hex. And I have that over here in the memory viewer. And currently, what that happens to be is this STA instruction. So this is similar to that slide we had before. So we have the opcode right here, 99 hex, and then we have the least significant bit, the 34, and the most significant byte, most significant byte, 12. So as I step through these instructions, you're going to see the memory values over here change. So I'm going to press F7. So the first thing we're going to do is we're going to load the 00 or over this where it says 34. And then the next one, we're going to store 4 where it currently says 12 in memory. So now we change the memory location over here. And now that the STA instruction has a different argument. However, you might notice that it didn't change over here, and that's just because CBM Purity Studio is not set up to really handle self-modifying code 100%, but it does work. So if I press F7 now, I have this index and initial variable of the A register, just like the previous example. Once I get to the STA function, even though it says hex 1, 2, 3, 4, if I press F7, look what happens to the screen RAM. It changes to an A. So the whole reason why we're doing this, it pays off by looking at this last instruction now. Now it only says 5 cycles opposed to 6. So if we let this whole thing run through, which will go through each character, we would have saved a total of 255 cycles. And this is, again, one of the big keys of programming assembly that you kind of just need to start learning. But learning it very early on gets you really good at it, and it lets you write really efficient code. Okay, I know we're starting to run low on time, so what I'm going to do is I'm going to skip this one example because it's kind of like built upon on this other example over here about printing strings. So what I'm going to do is I'm going to just talk really briefly about subroutines real quick. So I have a subroutine over here called print, and what this is doing is that it's similar to that loop with self-modifying code, but instead what it's doing is taking these arguments over here. So what you can do is that with a subroutine, it'll let you call a bunch of rules or instructions multiple times. So it lets you to have what's known as modular code. So you don't have like duplicate code all over the place. So in this case, what I want to do is I want to print a string. So a string is broken up by, can be declared as a byte. However, CVM Pure Studio lets you use these double quotes to indicate you're signifying a string. And then we're going to put, I just have this 0 byte here at the end to indicate what's known as a terminator, meaning it's the end of the string. So I'm going to be passing in the low and high bytes into the X and Y register, and then I'm going to call this print subroutine, which is declared down here. And a subroutine is simply just declared, you just create another label over here, right? And just make sure there's an RTS somewhere at the bottom so it returns. But in this code, since I'm going to be using the self-modifying technique, I'm going to take the value of the X register and I'm going to store it at loop +1, which so happens to be this, that's going to be the low byte of this hex 123 address. And then I'm going to store the Y argument as the high address of this 123 hex. And then I'm going to set a starting address, and then I'm going to start this loop. And what this loop's going to do, it's going to print all the characters on the screen. Now, how it's going to do that is it's going to call a kernel routine called chout. I have declared up here as a constant the address location inside the kernel of where it's going to print a character. And then I call I and Y, which will then increase the offset register by 1. And it's going to continue looping until either it encounters the 0 byte because of this BEQ up here. If it encounters a 0 byte character in the string, it's going to exit out. Or down here, it's going to exit out if Y is greater than 255. It loops around. So I'm going to run this example. I'm going to run it in an emulator. And what this thing should do is just print hello and then world. There you go. Now, if you notice in this example, I didn't have to type the sys command. And the reason why is because CVM Pure Studio has a tool to generate the basic instructions. So if I press list, there's my sys call. All right. So in this last example, I'm going to show you just real quick how to print a new line. So I'm just going to run this program, just see what it does first. So it prints Commodore 64 rocks. So if I want to print a new line, there's 2 ways to do this. So the first way to do it is you can create a new subroutine which passes in a string we declare as new line. So this D hex, this is the new line constant, and call the existing print subroutine. We could do that. It will work. However, it's very expensive in terms of cycles. This whole thing, like I already did the calculation, takes about 56 cycles to run. However, if we do something different, if we instead just call the kernel routine directly with a new line constant, which we'll declare up here at the top, which is just the D hex, that only costs 6 cycles. So printing a new line at that point is much faster. And CVM Pure Studio lets you create something called a macro. And what a macro does, it'll replace those 2 lines of code anywhere in my program when I compile it, as long as I indicate this print new line label. So first thing you do, you just have to declare a macro. You have to put this def-m argument, not argument, but directive first, and then the label, print new line. And then you have the 2 instructions that you want to replace in your code, and then you have end-m directive. So in other words, right here, I want to print my new line. I'm going to press F5. And real quick, I just want to show the assembly dump of what happened. So up here, you can see the code looks similar to the left-hand side. But right on these 2 lines over here, there's the 2 lines of code I wanted inserted. And I'm going to run it in an emulator. And there you go, it works. Okay, so I know, again, we're running low on time. We're just basically almost done. So next steps, once you have the basics down, we're going to be talking about you want to get input from the keyboard or the joystick so you can respond to end user input. You want to learn how to do sprites or custom character maps. It's a really fun exercise, and CVM Pure Studio has tools built in to make that easy. You want to learn about interrupts, which allows you to execute code functions simultaneously from each other. Sound effects and music, the Commodore 64, again, arguably the best sound chip in the industry, and there's a ton of examples and libraries of how to play sound effects. And loading and saving data from a floppy disk is very useful when you're trying to save data on sort of a game or load additional assets that are too large to fit in memory. And that's it. So I outlined on the slide over here some additional resources that might be useful. There's the Commodore 64 Programming Reference Guide, which came with the Commodore. You can find the PDF on it online if you Google it. Retro Game Dev has an excellent book which shows you how to use CVM Fusion Studio and write a platformer. The C64 memory map, it's when you're ready for more advanced stuff, shows you what every byte of the Commodore does. Codebase 64, great resource for literally how to do anything in the Commodore. Free code, excellent tutorials, detailed examples. Lemon 64 forums has the huge user base. The Commodore 64 lives on forums. If you have a question, post it there. Lastly, there's my website. You can find all the slides that I mentioned here, as well as the code examples you can download. I have a link to my GitHub page where that information is stored. Just look for developing for the Commodore 64. And that's it. I am going to now switch over, turn my camera on, and let me know if anyone has any QA. Hello, everybody. Let me see. I'll go to the chat window also. Let's see. Are there any questions? I know we have not too much time left. Did I lose everybody? Okay, I see David looking at my website. Yes. Oh, yeah, that custom kernel I made. Yes, that is true. I did make a custom kernel. In fact, I am actually in the process of making what's known as movies with that. I've made a couple. I make a new movie like every week now for the last month. It's using the RAM expansion unit. It's definitely one good way to learn how to program on a computer is to write your own custom kernel. Don't recommend it for the casual programmer, but it definitely made me understand how to do a lot of stuff. I have a complete documentation in the docs folder, but on my website, actually forgot to mention, I have contact information on my website. You scroll near to the bottom if you guys need to reach out to me for any reason, email or Facebook. You can reach out to me that way. So I see we have 67 people in the chat. I think the session's going to end any second now. So again, if anyone has any questions, now's the time. Otherwise, you can copy that link at the bottom, the battalia.dns.net, to again link to the GitHub page, which will have this presentation as well as the coding examples, as well as ways they reach out to me. Okay, it's 12:30 now. I don't know if I'm still on or not. Oh, I am still on. Okay, great. Excellent. So David, you have an event later on tonight? I know, David. I saw that you had. I watched that whole. By the way, that Commodore series you did, absolutely fantastic. I wouldn't even know where to begin to get all that time to put together like a huge educational series just like that. It was amazing, and I really appreciate that in-depth coding stuff when you talked about creating Planet X2. It was amazing. I really got. The best part was when you showed that it's not a sprite maker, but that character creator where you create the custom characters. It was great. Yes, there is a delay. I think Ryan said it was like 10 to 15 seconds. Yes, there is a delay. He said that it was similar to, I guess, the Twitch. I've never hosted on Twitch before, but I know that I've chatted in Twitch a lot, and it's definitely been like that for sure, where there's a delay. There's a Q&A session here on the right. I don't see anything posted there. I'm hoping it's working. Oh, there's one answer. Here we go. Roman, I'm trying to pronounce your name correctly. Warner, have you ever created a C64 game yourself? No, I have not created a C64 game myself. I do have the book right here. This is the book I recommend. It's maybe backwards on your screen. This is the Retro Game Dev. I definitely want to start doing it. All I've done really is create movies. I do have a YouTube channel. Maybe I can share real quick one of those movies in the chat. I might have to turn my screen off real quick because there's sometimes there's issues with that, but maybe not. Let's see what this does. I've never created a game myself. It's definitely on my bucket list for sure, and that's actually one of the reasons why I created that kernel that David posted in the chat. I have my own C64 kernel, which kind of like builds on top of the existing C64 kernel, but it has the ability to has a lot of like libraries and stuff that either I wrote or I copied from Codebase 64 and other places. Again, Lemon 64 is amazing. I had tons of questions on the Commodore, how to program on it, even setting it up, like hardware questions, and they are amazing. Okay. Here's a good one. Let's do the Simpsons. So before I start on this, so again, this is running in let's see. Sorry. Just switching screens. Okay, so this is written in my custom kernel, and it uses what's known as the RAM expansion module. I don't want to get too much into the details of the RAM expansion module for the Commodore 64, except that is by its name, it lets you expand the RAM. One of the amazing features about the RAM expansion module is that it loads data extremely fast, so fast that you can actually display graphics and sound in a very fast manner. So people have already discovered this is nothing new. This is discovered, I guess, some years ago, and people create what's known as movies. And I started playing around with this myself, where a person on Lemon 64 about a month ago posted a video of the AHA music video, Take On Me, and I was intrigued, and I talked to that person in terms of figuring out what things get involved, and me when some other developer created a tool to create movies. And so here's one right here. So this is running in the Vice emulator. And what this is, you can see, it's the intro to The Simpsons, season 1 specifically. Now there's sound to it, although the sound is not coming over the think, you know what I should do? Let me just put the link in the chat. That's what I should do. So you guys can take it yourself. And this will run on an actual Commodore 64. Someone on one of the Facebook Commodore 64 groups was able to get this to run on an actual Commodore 64. However, he needed the help with the Ultimate Cartridge 2, which is, I believe, 139 euros. So whatever that is in dollars, I don't know. And the RU, the RAM expansion module, allows you to have up to 16 megabytes of RAM. And this RAM is not directly accessible by the CPU, so you have to like load in like chunks of memory into the Commodore 64 RAM and then have it like, you know, either play it or display that information. So in this case, what I'm doing is I'm literally taking what's known as a koala file, which is a multi-color image file. I'm displaying it into the video RAM directly. And as far as audio is concerned, it's using a digi format, which is like a 4-bit, 4 kilohertz type of pulse modulated code audio. Everything's uncompressed. And as you can imagine, it sounds not the best. I mean, if you watch the YouTube video, you'll get the full experience.